Hello friends, welcome back. Last time we met the divergence, the operator that takes a vector field and asks, where are the sources? Today we meet its sibling, the curl. Curl also takes a vector field as input, but instead of a scalar, it returns another vector. The curl at a point measures how much the field circulates locally, how strong, and around which axis. Here is the picture. Drop a tiny paddle wheel into the field at a point. If the field pushes the paddle around, the curl is non-zero, and the curl vector points along the rotation axis by the right-hand rule. If the paddle stays still, the curl is zero. The field is irrotational at that point. Why do we care? Two reasons. First, in electromagnetics, the curl appears in two of Maxwell's equations. Nabla cross E equals minus partial B over partial T, and nabla cross H equals J plus partial D over partial T. Curl talks about how a changing magnetic field makes electric fields swirl, and how currents make magnetic fields swirl. Second, curl tells you whether a field is conservative. If curl A is zero everywhere, you can write A as the gradient of some scalar potential. Path integrals do not depend on path. That is exactly what makes voltage well defined in electrostatics. The curl is built from a determinant. In Cartesian, nabla cross A is the determinant of a 3x3 with x hat, y hat, z hat in the first row, partial x, partial y, partial z in the second, and ax, ay, az in the third. Expand by the first row and you get the standard form, partial az over y minus partial ay over z in the x hat slot, and so on by cyclic permutation. In cylindrical, the determinant works the same way, but the rows pick up scale factors. The first row has unit vectors, the second has the partial operators each scaled by the appropriate length factor, and the components in the third row are also scaled. The shortcut. For any orthogonal curvilinear system, the determinant has length factors h rho, h phi, hz on each row, and you divide by their product outside. In spherical, the same template gives the radial unit vector with 1 over r squared sine theta out front, the theta term with 1 over r sine theta, the phi term with 1 over r. We will not memorize each line, we will look it up and apply it. What you should remember is the cyclic pattern x to y to z, the determinant structure, and the rule that wherever a length factor sits in the volume element, it sits inside the curl too. Worked example 1, Cartesian. Take exactly the same A from the divergence example, A equal to x squared yx hat plus y squared zy hat plus z squared xz hat. Same field, same point, p equals 1, 2, 3. We will compute curl A and see what new information it carries. We need 6 partials, 2 per component of the answer. X hat slot, partial az over y minus partial ay over z. Az is z squared x, partial with respect to y is 0. Ay is y squared z, partial with respect to z is y squared. So the x hat component is 0 minus y squared, which is minus y squared. Y hat slot, partial ax over z minus partial az over x. Ax is x squared y, partial with respect to z is 0. Az is z squared x, partial with respect to x is z squared. So the y hat component is 0 minus z squared, which is minus z squared. Z hat slot, partial ay over x minus partial ax over y. Ay is y squared z, partial with respect to x is 0. Ax is x squared y, partial with respect to y is x squared. So the z hat component is 0 minus x squared, which is minus x squared. Put it together. Curl A equals minus y squared x hat minus z squared y hat minus x squared z hat. Evaluate at P, where x equals 1, y equals 2, z equals 3, minus 4x hat minus 9y hat minus 1z hat. And here is the message. In the previous video, we found divergence of this same A at this same point equals 22. And now its curl is non-zero. Same field, two completely different measurements. One says the field has a source-like outflow, the other says the field also rotates locally. Divergence and curl are independent windows into the same vector field. Worked example 2, spherical. And again we reuse the field from the divergence example. A equal to 1 over r squared in the r hat direction. The famous inverse square radial field, the electric field outside a point charge. Find the curl. The spherical formula has 3 terms, but A has only an r hat component, and that component depends only on r. Look at the 3 terms one by one. The r hat term involves partial derivatives of a phi and a theta. Both are 0, so the r hat slot is 0. The theta hat term involves partial of ar with respect to phi and partial of r times a phi with respect to r. Ar depends only on r, so its phi derivative is 0. A phi is 0. The whole theta hat slot is 0. The phi hat term involves partial of ar with respect to theta and partial of r times a theta with respect to r. Ar has no theta dependence. A theta is 0. The whole phi hat slot is 0. Conclusion. Curl A equals 0, everywhere with r greater than 0. The inverse square radial field is irrotational. Now feel why this matters. In the previous video, we showed divergence is 0 of the origin too. So outside the point charge, the electric field has no sources and no curl. The second condition is exactly what guarantees a scalar potential V exists. And indeed, V equals 1 over r, minus the gradient of 1 over r is 1 over r squared in r hat, which is Ra. The Coulomb potential exists because curl is 0. The Coulomb integral is path-independent because curl is 0. Pretty much every clean result in electrostatics rests on this one fact. Quick recap. Curl turns a vector field into another vector. It measures local rotation. Magnitude is twice the angular speed of a tiny paddle wheel. Direction is the rotation axis by the right-hand rule. The formulas come from a determinant. In Cartesian, x hat times partial az over y minus partial ay over z plus the cyclic permutations. In cylindrical and spherical, the same determinant template includes the length factors h rho, h phi, hz divided out front and inside the rows. 2 answers. Cartesian, A equals x squared y x hat plus y squared z y hat plus z squared x z hat at P1, 2, 3. Curl A equals minus 4x hat minus 9y hat minus 1z hat. Same field had divergence 22 at the same point, 2 independent measurements of the same vector. Spherical, A equals 1 over r squared r hat, curl A equals 0 everywhere off the origin. The inverse square radial field is irrotational, which is why a scalar potential V equals 1 over r exists. Electrostatics rests on this. Next time, the divergence theorem, the integral form that ties divergence at every point to the flux through a closed surface. See you then.